Hello, my name is Carlos Tavares and I come from the Center of Physics at the University of Minho in Portugal. The title of my talk is Transparent Thermoelectric Titanium Dioxide Doped Niobium Thin Films. We envisage to apply these materials as transparent thin films which can harvest thermal energy from the environment and convert this into electricity. For example, here in this graph, you can see the estimated US energy consumption last year from all of these different sources. You can see that the rejected energy is about 2/3 of this whole produced energy, which is quite a lot. And even worldwide, 66% of energy is wasted as heat. If we could aim to at least recover 25% of this using thermoelectric materials, we would be doing a good job to our planet. So when we want to quantify the performance of these materials, it's important to calculate the thermoelectric power factor. And this thermoelectric power factor is equals the square of the Seebeck coefficient multiplied by the electrical conductivity. And this power factor is also included in the ZT figure of merit, which is another parameter which can help to compare the performance of thermoelectric materials. So it's actually this ZT figure of merit is the power factor divided by the thermal conductivity, which should be as low as possible at a specific temperature. And since these are transparent thin coatings, it's also important to measure the TCO figure of merit for these metal oxide films. It's just the average transmittance in the visible region to the power of 10 divided by the sheet resistance. So the main objectives for these coatings is that they have to be optically transparent, they have to be electrically conductive, thermally resistive, have a high Seebeck coefficient, a high thermoelectric power, and a high figure of merit. We produce these coatings in reactive mode. We use oxygen. We can either do it from two different metal targets or from a titanium niobium composite target with about 5% in weight of niobium. And our substrate holder has 5 individual substrate holders. So in one batch, we can do 5 different series of films. And we can load about 5 or 6 samples in each individual substrate holder. These films have a very high transmittance in the visible region. You can see here for 2 different coatings, one with 120 nanometers and another one with 480. And for the thick one, we have about 71%, the average transmittance in the visible region, whilst for the thinner one, it's about 88%. We have a thermoelectricity setup where we can measure the Seebeck coefficient of our films, and we do this in vacuum. It's a custom-made system that we did in-house, and we have the software and hardware in order to control and take the measurements. So basically, we need to have 2 Peltier systems, which are under these copper blocks, one for cooling one edge of the film, another one for heating. And here is our substrate with our sample with a film on top. It's transparent. And after applying a thermal gradient between the edges, we measure the potential, and then we can acquire the Seebeck coefficient. So this is the software that we used for ramping up the temperature and controlling the potentials. Before producing these films, we needed to know in which were the best conditions for the reactive sputtering. So we just we made a dummy experiment where we increased the oxygen during reactive sputtering, and then took away all this oxygen in crucial steps. So we could have this kind of hysteresis curve and try to see where the films will be more metallic or more insulator, so where the oxide phase is more present. And in between, we would have an optimized window. And this gray area here, which is between 6 and 8 SCCMs for oxygen inlet, is actually the zone where we produce the films which have a better thermoelectric performance and a best compromise between electrical resistivity and thermoelectricity. Because below the films, below this threshold window, the films will be in metal mode. They will be perhaps too opaque with very low transmittance, and above they will be very insulating films, which would be not ideal for our thermoelectric systems. So here you can see the the electrical resistivity in ohms centimeter as a function of oxygen inlet into the system. And so for this optimized window, we have the best compromise of electrical resistivity. and the films have an average value of around 10 to the minus 1, 10 to the minus 2 ohms times centimeter. And doing annealing, it doesn't really change very much the electrical resistivity of films, except for the case in the oxide mode, where the films as deposits are very insulating, and only after thermal annealing we can have electrical resistivity of the order of 10 to 10 to the minus 1 ohm times centimeter. The surface morphology of the films, it has this particular dome rounded shape because the films develop a columnar structure, and you can see here this kind of features on the surface. So we did the measurement of the Seebeck coefficient for all these films for different oxygen inlet during deposition, and you can see that this optimized window between 6 and 8 SCCM of oxygen, we have the best performance, where these films can obtain almost a value of minus 250 microvolts per Kelvin. It's negative because the titanium dioxide is an N-type semiconductor. And this is really related with the crystallography nature of these films, because below this window here that we have below 6 SCCMs, the films are mostly amorphous with very small anatase rutile diffraction peaks. In this optimized window, both anatase and rutile phases become more crystalline. Rutile is more abundant at around 7.5 SCCM. And when we increase the oxygen inlet, it reverses, becoming anatase more relevant than rutile. In order to measure the thermal conductivity, which is really important to know if you want to calculate the figure of merit, and it's very difficult to really measure the thermal conductivity of the film without the influence of the substrate. So we choose to do a frequency domain thermal reflectance with 2 lasers, and we did this at the ICMAB Institute in Barcelona, Spain, under the guidance of Professor Alejandro Goni and Sebastian Raparaz, which were very helpful. And we could measure the thermal conductivity both as a function of the thickness of the films and as a function of the oxygen, which is inlet during deposition. And for the optimized conditions between 6 and 8 SCCMs of oxygen, we have a stabilization of the thermal conductivity at around 1.5. So this is 1.5 watt per meter per Kelvin. When you look at the data as a function of thickness, we see that for the thinner films, we have a very low thermal conductivity, about 0.5, which increases up to 2.5 for the thicker films, around 700, 800 nanometers. In order to check if we are producing niobium oxide phases, we did X-ray photoelectron spectroscopy, and we looked at titanium 2P, niobium 3D, oxygen 1s score levels. When we look at niobium 3D and take into account the spin orbital splitting, and from the positions of the binding energies of these 2 peaks, we can see that it indicates that we're not forming the niobium oxide, and so it's more clear that niobium is substituting titanium in the anatase structure. Similarly with the titanium 2P peaks, because this is typically of titanium dioxide, both there the separation, their binding energies, and also for the the oxygen 1s score level, we can see that the main peak at 530 electron volts is ascribed with titanium oxygen bonds. So the insertion of niobium into the lattice, which is really below 2 atomic percent, so that the films maintain their transmittance, does not really change the balanced state of oxygen here or the binding energy. To further study the local structure in titanium dioxide when we dope niobium, we did some X-ray absorption experiments, and we did this at the synchrotron at DESI in Hamburg. And here you can see the EXAFS spectra and the corresponding on the right Fourier transform for both titanium K edges and niobium K edges. So basically we just tuned the X-rays to both the titanium KH and niobium KH and looked at the local structure around these main cations. So for the titanium H, here you can see we did this at 18 Kelvin. If you look at the black curve, which is for the titanium dioxide niobium film, you see that it matches better that of the anatase reference powder, which is the blue line. So we see that the titanium dioxide niobium films, they retain predominantly the anatase structure. And from this, we can also calculate the bond distance between nearest neighbors of titanium, which is the oxygen and niobium. And you can see that the black data really fits very well that of the titanium dioxide anatase powder. Even to a longer distance, that around 10 angstroms, we can see that these successive coordination shells, they fit very well the data. For niobium, it's the same. We have a very good fit when we compare our film, which is the black lines, with that of anatase reference powder, which means that niobium is bonded to oxygen in the anatase structure and not in some kind of niobium oxide. So, because the niobium oxide standard powder is the red line, and it does not fit very well the data of the titanium dioxide doped to niobium thin film, which is the black data. And again, we can see that there's a very good fit for longer distance from the main cation, which in this case now here is niobium. We did this here at 300 Kelvin, and it can go all the way up to 10 angstroms. We did some, based on this data, we did some further reverse Monte Carlo models where we tried to determine the bond distance of the different elements. And we started off with the titanium dioxide 5 × 5 × 2 supercell at 300K, and we did for two types of dopings. In the left, we have for 5% of niobium inside the anatase, and on the right, for about 10% of niobium within anatase. And here you can see on the black line is titanium oxygen bonds, and the green line is niobium oxygen bonds. So if we concentrate here, for this main peak, for both cases of doping, we can see that the black line for titanium oxide bonds is not splitted. So we have a peak at around 1.95 angstroms, which is associated with titanium oxygen bonds in anatase. While if you check the distances for niobium oxygen, you see that it's splitted. So both titanium and niobium atoms are octahedrally coordinated with oxygen. But in the case of niobium, it's actually 3 + 3 atoms instead of 6 atoms for the case of titanium oxygen, and that's why the peaks here are splitted. And when we look at the titanium bonds here at around 3 angstroms, and at the niobium titanium bonds at around 3.4 angstroms, we can see that these two the red curve and the blue curve is slightly shifted. So it means that for the case of niobium, due to the different ionic radius, the lattice is a bit more relaxed, and so the distance does not match really well. But nevertheless, we can see that niobium is substituting titanium inside the anatase structure. So the last slide is a small video where we did an experiment where we put one of our films here on a glass slide. We put the one side at room temperature was about 18 degrees C, and the other side on a copper block immersed in ice, so at 0 degrees C. And you'll see in this experiment that from this 18 degrees gradient, we can see the development potential here in the microvoltmeter that we see here. And furthermore, when somebody touches the surface of the thin film, you'll see an increase in potential, which means that the body heat is transferred into the sample despite the person using gloves. You still have a gradient of temperature, which is moving into the film. And then we develop a different potential difference between the edges. And here we calculated the Seebeck coefficient of around minus 145 microvolts per degree or Kelvin. So with this, I conclude my talk. Thank you very much for your attention. I would just like to thank my PhD students, Joana Ribeiro and Felipe Correa, and be grateful for FCT for their PhD grants. And thank you very much for your attention. If you have any doubts, any questions, you can just send me by email, or perhaps we can find a way to chat around any specific topic that you might have. Thank you very much. See you next time.